What you're looking at here is a logic-based 8-bit calculator I built from scratch because I have too much time on my hands. It comes in at 7 pounds, 26 by 16 inches, and only had 4 bytes of data. The calculator itself can do operations, just the basic 4, with any two numbers between -99 and 99. And just as a precursor, this video will not be super in-depth, but rather just will serve as a way to show off the creation I spent 2 years working on. I began this project after I came across a program named Digital Logic Sim created by Sebastian Lame. This program allowed one to view the inner workings of circuits that the user builds from logic gates. What are logic gates exactly? Basically, they act as truth tables, and the most basic gates do it their name suggests: AND gate, NOT gate, OR gate, etc. Systems that are then built from logic gates are then called logic systems, and at a fundamental level, all computers are built from logic gates, and my calculator is no different. For example, say you have two inputs and you only want your output to turn on when both your inputs are on. This would be called an AND gate, a type of logic gate. This program made it possible to get things all fleshed out before building this project. And after a year of working on the design, I finally had myself a working product that was built strictly on logic, which even included division, arguably one of the most complicated basic math operations. But before going any further into the workings of the calculator and the system of it as a whole, binary must be understood. The calculator itself is split into 8 units, and all have to do with binary in some way or another. Take 99 for example. In binary it's 1 1 0 0 0 1 1, where 1 is on and 0 is off, and these 1s and 0s can be thought as lamps being turned either on or off. Binary is a system of powers of 2s, which might sound complicated, so just imagine each piece of data being worth double the amount of the previous number. When a piece of data, a bit, is on, then this represents a number, and the sum of all these numbers that the bits represent is equal to the value you want in binary. And this works for all numbers between 1 and 127, the largest number you can represent with 7 bits. So here it's 58, 105, and 9. It is in this form of information that computers are able to take data and transform it into something new and useful. However, these examples only include 7 bits of data, as one can see in our example of 11000011. And seeing as this is an 8-bit calculator, where is this 8th bit of information coming from? We use the 8th bit as the sign bit, allowing our calculators to represent both positive and negative numbers. This lets us represent 99 as -99. Giving us the 8th bit of data to work with, making this an 8-bit calculator, where 7 bits of data are dedicated to the number, and 1 bit is dedicated to the sign, thus 8-bit. Going back to a block diagram, everything begins at the number encoder in memory. The first thing the calculator does is takes a number input, such as 99, and encodes those button presses, 9 and 9, into binary. It then stores the 8-bit number into the memory, and the system waits for an input from one of the operation buttons. Once one of those buttons has been pressed, it repeats the process of taking another new number and encoding it before sending it to the calculated memory. The control unit, once the equals button is pressed, then tells the data router which unit to send the two 8-bit numbers to, the multiplication, division, or addition and subtraction unit. The system then grabs the outputs from all of these units and combines them into a single output via the data collector/multiplexer. This then results into an output of up to 14 bits plus a sign bit after the operations are completed, and this is then sent to a binary to BCD converter. This might sound complicated, but all this part does is break the 14-bit number along with the sign bit into its individual parts, that is, the 1, the 10, the hundreds, and thousand places. So 99, or 11000011, will then turn into 1001 and 1001, which can then be interpreted and displayed in the display module. Once all is said and done, you have a calculator. And an expensive and really horrible one at that. It contains 118 IC chips, which are the building blocks that connect everything together, and almost 200 resistors. The IC chips, for reference, are the little black things on the circuit boards. For the memory, it contains just 4 bytes of data, with 1 byte equaling 8 bits of data. On average, most computers have about 17 billion bytes of data, or 16 gigabytes. 2 bytes of the calculated memory are dedicated to the division unit. The division unit can display both the quotient and, with the press of a button, the remainder. But enough yapping. Looking at the actual thing, when we do number inputs such as 9 plus 9, we get 18 as expected. Or something a little bit more complicated, such as 99 plus 1, we get 100. Or 99 plus 99, 198. Or 65 minus 7, we get 58. Or if we do negative 9 minus 9, then we get negative 18. 8 times 9 is 72. Or 99 times 99 is 9,801. Moving on to the division, doing 99 divided by 2, we get 49 with a remainder of 1. Or doing 56 divided by 12, then we get 4 with a remainder of 8. And the example persists. It's a calculator. Do any two numbers between negative 99 and 99, pick your operation, and it will calculate the answer beautifully every single time. Beside your number and operation buttons, you have an equals, reset, and sign button, and that's it.
That's about all there is to it. I hope to release a technical video on this project within hopefully the next year, and if nothing else, I do have a few other projects in mind that are pretty complicated as well, but till then I'm gonna go burn a bunch of IC chips. I've had too many wiring issues